Hi, Eddie. Good afternoon.
Hello,
Hi.
Dr. Ko.
Hello there.
Good to see you. Thank you for joining.
Oh, you're welcome. I'll only be here for a short time.
Yes.
Um, I'm sure Gina's in great hands.
Thank you. And we are so excited about this presentation too. And students are still talking about your presentation. Thank
That's
you.
awesome. I want to share this with you before Gina joins us, is that she was on CNN recently. She was on NASA's TV for the last eclipse, and she's gonna be on NASA TV for on Monday. So Gina is really the celebrity of heliophysics. Anti's the director, and he's a
Okay.
celebrity in his own right,
Okay.
but Gina's just a rock star. So
Okay.
it's great that she's here, and also too, for her making the time to do this. She's so busy right now. I can't even imagine what she must be going through. And I know she's traveling tomorrow as well. So Gina's here. Hi, Gina.
Thank you so much
Hi.
for making the time. Thank you
Of
so much.
course. Yeah, no problem. I'm excited.
So we will have a student moderator for your session. We try to encourage our students to learn and interact. And Mr. Clint Hinostroza is here. Clint,
Great.
welcome. And now I will hand it over to you. Okay. And thank you again, Dr. DiBraccio. It
Of
is.
course. Yeah, thank you for having me. I'm glad this worked out. So thanks to Eddie too.
Yeah, thanks to Eddie, big time. Thank you.
You're on mute, Clint.
Clint, you are on mute.
Oh, it doesn't look like he is. Maybe there's a
Yeah, it
double
doesn't look.
unmute.
Can you hear me now?
Yes, we
Yes.
can hear you now, Clint.
Good afternoon, everyone. Dr. Gina DiBraccio, it's a pleasure to meet you. My name
Hi.
is and Mr. Gonzalez too. My name is Clint Nostroza. I'm a PGCCS student majoring in civil engineering. I will be the moderator for today's session, and thank you so much for joining us today.
Definitely. I'm excited to be here. So should
Okay.
we make sure I can share my screen properly and everything?
Yeah, we can do that. We can practice sharing your screen.
Okay.
I
That's
see
good.
it.
You should
Yep.
see that, and I'll test the presenter mode. Does that look good?
Looks good.
Yeah.
Okay. Let me remind myself how to hide these. Hide the video panel. Okay. No, that's not what I wanted.
Yeah, Gina, all we see is slide one. I don't see any notes or anything else on the sides of it.
Okay, good. Yeah, I just see all the little Zoom windows popping up, so I'm trying to move them out of my way. And then, okay.
Yeah, I think we're good.
And
Awesome.
Clint,
Can you hear? Okay. Yeah. Good afternoon, everyone. My name is Clint Nostroza. I'm a PGCCS student, and I'm majoring in civil engineering. Today, I'm honored to serve as your moderators for today's session on Heliophysics Big Year. Before we delve into the heart of the presentation, I'd like to take a moment to express my gratitude to each and every one of you for joining us today. So before we proceed further, I encourage each of you to participate in our session by asking questions. You can use the chat feature or the raise hand button at the end of the presentation. Also, don't forget to complete the survey at the end of the presentation too. The link is located in the in the chat box. So once again, I want to extend my warmest welcome to everyone gathered here today. So let's start. It's my pleasure to introduce our esteemed guest speaker for today's session, Dr. Gina DiBraccio. Dr. Gina DiBraccio is the Deputy Director of the Heliophysics Science Division at NASA's Goddard Space Flight Center. Her research focuses on magnetospheric physics and solar wind planetary interactions for both intrinsic and induced planetary magnetospheres throughout the solar system. More specifically, Dr. DiBraccio studies the transfer of energy through space plasmas and magnetic fields through the analysis of in situ data of various planets. Using a comparative planetology approach, her research and publications have involved Mercury, Mars, Jupiter, Saturn, Uranus, and Neptune. Dr. DiBraccio received her Ph.D. in space science from University of Michigan's College of Engineering. Her thesis work investigated magnetic preconnection and space plasma dynamics throughout Mercury's magnetospheres. She also holds a master's degree in atmospheric and space sciences from the University of Michigan and 2 bachelor's degrees from the University of Pittsburgh in physics and astronomy and business administration. Dr. DiBraccio will tell us about the exciting things that are happening in Heliophysics Big Year. In addition, we welcome Dr. DiBraccio to share more of her esteemed journey if she wishes to do so. So, Dr. DiBraccio, the audience is all yours.
Great. Thank you, Clint, for that wonderful introduction. Hi, everyone. Thanks for joining today. I'm going to take a moment and share my screen. But as Clint said, so I'm here to talk about the Heliophysics Big Year, but I will actually start out by just talking to you all about my path to NASA and my career path, because I'm always happy to share that experience and answer questions too, especially since all of you are working on your degrees right now. You might have some questions about that. So let me pull my slides up for you. And I will get those in presentation mode, so they should be good to go.
Yeah.
Okay. All right. So yes, we'll be talking about the Heliophysics Big Year, but the first thing that I want to do is get into my career timeline to just kind of give you a sense of the path that I took to get to the position that I'm currently in at NASA. And so these are some questions that when you see these questions, what do you want to be when you grow up and what path should you take to get there? People often think about this as something that you ask a kid that's younger or in grade school, but this is something that I continually ask myself, where am I currently and what do I want to be when I grow up? Because for me, it's always kind of growing and changing and deciding what the next direction is. And so there are always many different paths to get to a certain place, and you'll get to a point in your career where you have decisions to make. And so these are always questions that I'm asking myself. But for me, so I went to the University of Pittsburgh for undergrad, and I got my bachelor's of science in physics and astronomy, as you heard in the introduction. But I also got another bachelor's degree in business administration. And when I did this, it was honestly because I was interested in all of these topics, and I'm a person that really has interest in a bunch of different areas. And so I like to try out many things to figure out what I like the best. And at Pitt, there was an opportunity for me to get this business degree without having to take, all of the required courses to add on years and years. It was something manageable. So I ended up getting my undergraduate degree in 5 years after I added this on. Fast forward to where I am now, and I didn't even have the foresight to know just how valuable that business degree would be for me, because a lot of the work that I'm currently doing, even though I'm a scientist, also has to do with managing finances and budgets and working with schedules and, of course, running teams and people. And so that degree actually was much more useful for me than I could even imagine at the point when I was getting it. So before I finished undergrad, I tried to get an internship, and I had no idea, what my chances were or where I would intern. But I submitted something like, I would say, at least 10 or 11 applications for different internships all around the country. And as it turned out of all of those that I submitted, I got one. And that's all it takes, is that one, because that one for me was at the NASA Glenn Research Center, which is located in Cleveland, Ohio. So I had an internship there for a summer. And when I was there and I was doing the internship, I took that opportunity to meet with different people, go see some work that was going on in different groups, and really see what options NASA Glenn had, but also NASA as a whole. And I was able to turn that internship into what they called the co-op program. It's now called the Pathways program at NASA. But what that is that I became a civil servant as a student. So I was a federal employee as a student, and I would alternate semesters of working at NASA and then taking classes. So I stayed at NASA Glenn after my summer internship ended. I stayed through the fall, and I became a co-op student. And during that time, I was doing really interesting work where I was basically helping to test engines in a lab, and these engines were run on plutonium for actually really long missions, because the lifetime of plutonium, it decays very slowly. So you can use that as a power source for NASA missions going deep into space. But as I was doing this work, I thought, okay, I realized that the engineering aspect might not be as much aligned with my career goals as the science is. And although I understood the importance of, understanding these engines and how they work and making them better, I found that probably wasn't the path for me. So what I did was I actually transferred my co-op position over to the NASA Goddard Space Flight Center, which is in Greenbelt, Maryland, also the same place that I work now. And I transferred it over there because I was able to get an opportunity to try out some science. So I moved over to NASA Goddard, and I started working in the Heliophysics division, which ironically is where I currently am. So I started there back in 2009. And you'll hear about the other parts of my journey, but I came full circle, and I'm back to the same division at the moment. But once I got into the heliophysics science division, I started learning about some of the work with plasma in space and how the sun impacts the planet. And as soon as I started working on that, that's where I realized that I found my niche that I was really interested in. So from there, I enrolled in grad school, and I continued my co-op for a while. And I went to graduate school at the University of Michigan, where I got my master's in atmospheric and space science, and then I got my PhD in space science. Now, I spent 5 years at the University of Michigan, and you should know that when you enroll in a PhD program like this, the master's degree is part of it. So I didn't have to enroll in a master's degree and then do my PhD on top of it. I spent 5 years there. It was 2 years of classes, 3 years of research, and it can vary depending on the programs, but that was my experience at the University of Michigan. And I'm happy to answer questions about, deciding if grad school is right for you as well. One thing that I will note that I had no idea about when I was looking for grad schools was that when you're going to get your PhD in this type of science, there are grants that the professors have that will cover the tuition for you, and they generally will give you a living stipend too. So I already had student loans from undergrad that I knew that when I went to grad school, I probably wouldn't be able to go if I had to take out more student loans. And lo and behold, I actually got a living stipend that was quite reasonable for grad school. So that's something that I had no idea about. Nobody ever told me. So I wanted to share that with you. Now, after I finished and I got my PhD, I got a postdoc position at the NASA Goddard Space Flight Center. So during the time when I was in grad school, I ended up coming out of the co-op program and just staying at the University of Michigan for the last few years. But I knew that I really enjoyed the work that they did at NASA Goddard, so I knew that I wanted to get back there somehow. So there's a program called the NASA Postdoctoral Program, NPP, and you write a proposal to say, this is the type of science that I want to do. My proposal got selected, and I went back to Goddard for a postdoc. And in fact, when that proposal was selected, it was for me to work on NASA's MAVEN mission, which is currently orbiting Mars. And as I joined NASA Goddard back in 2014, this time, MAVEN was just getting ready to go into orbit about Mars. So MAVEN is coming up on its 10-year anniversary orbiting Mars. And that also marks my 10-year anniversary of being back at Goddard as well. So after several years of being a postdoc and working through some different positions at NASA Goddard, I was hired on as a civil servant again, so a federal employee. I'll talk a little bit about the work that I've done along the way, but this is just kind of, the timeline of where I've gone in my career. Now, so this is the highlights, the milestones that I've explained to you. But I want to show you, I'm throwing a few X's up here because what I'm not talking about are the times where I've said no or the times that I've failed at different opportunities. And I do want to take a moment just to highlight that although I'm talking about all of these successes and achievements, it's not to say that there weren't any bumps in the road or, any times where I questioned what I was doing or had failures. In fact, there were plenty of those to go around. I'm sure I can tell some great stories about my failures as well. But I think the point that I'd really like to make here is that I would argue I've learned more from the times that I've failed than the times that I've succeeded. Because when I fail, it really forces me to take a step back and consider, what went well, what didn't, what would I change for next time, maybe alter my trajectory a little bit. And there are still times right now where, I try for different opportunities and it doesn't work. So there will always be bumps in the road. And for me, it's just, how do you handle those? And how do you either course correct or just use that kind of as leverage to really motivate yourself to continue forward? And so this is my position today. I am the Deputy Director for the Heliophysics Science Division at NASA Goddard. Our division consists of about 400 people. Most of them are scientists, but we have engineers who help us to build different instruments that we're working on. We have a financial team that helps us to work with our finances and balance our budgets and make sure we're spending our money. We have project support specialists who help us to keep our schedules in line and help us with a lot of our travel and other things. So it really takes a lot of people to make the work that we do successful. And so let me also just tell you what heliophysics is, since we'll be talking about that a lot more going forward. So heliophysics is the study of the sun and its influence on everything. And what that means is that we can study the sun, solar physics itself, but the sun is also giving off energy, and that energy can have an impact throughout our whole solar system. So all of our scientists are studying everything from the sun out to the depths of our solar system. In these pictures that I'm showing you here, we call this our WOW room. It's a really great panoramic screen where we get to show some of our beautiful images. You see here images of the sun from the Solar Dynamics Observatory mission. And actually, the group of people that I'm talking to in this room is a class of astronauts who were coming around to tour. So this is one of the fun things that I get to do as a part of my job, is entertain some of the higher level visits that we have and educate people on heliophysics, on space weather, which is activity coming off of the sun. So that's kind of a big part of my job today. I'm also the deputy principal investigator of the MAVEN mission. So I told you that when I did my postdoc, when I started as a postdoc back at NASA Goddard again, I was able to join the MAVEN mission. Well, I started as a postdoc, and over the last 10 years, my role has evolved over the course of the mission, where I am now basically, there's the principal investigator and I am the deputy to her. So almost kind of second in command for that mission, where I'm helping to lead the mission, lead the science, help to lead the team, and really explore some of the work that we're doing at Mars, which is a lot of fun. And if I had to kind of tell you the different pieces of the work that I do on a day-to-day basis, this is how I break it up in my mind. So I'm a scientist at NASA Goddard, and I perform science research, whether that means I myself am sitting down and analyzing data and analyzing the plots that come out with it, presenting my results, writing scientific papers, but I also advise grad students and postdocs myself. I have research scientists working for me, so I have a research team. Now, moving over to the right, you'll see I have experience with magnetometry instrumentation. What that means is these instruments that you see in the picture below, those are magnetometers, and magnetometers measure magnetic fields. So we build these magnetometers, we have engineers that build them for us, and we put them on spacecraft and send them out to space. And part of my job is to come up with ideas of where we want to measure the magnetic fields. And once we do, and once we have those measurements out in space, I get to look at the data that we send back from those. And then mission management. So we talked about my role on the MAVEN mission, really trying to make sure that everything runs smoothly with that we answer the science questions that we set out to answer. So that takes up a decent amount of my time too. And then finally, NASA management. That's my role in the heliophysics division, making sure that we're being strategic about the science that we are going after and supporting our whole group of scientists and engineers and everybody else that makes up our division. And then I also like to sprinkle in a little bit of a personal aspect here, because for me, this work is really fun. So this is my life, but this is also my work in a certain way. I like to tell everybody that I have a family. So you can see that picture of me with my husband and my 3 sons. And that's a really important message for me to give, because when I was interning at NASA Glenn, nobody in my group was married, nobody had children, which is absolutely fine, but I really questioned whether I would be able to have the career that I wanted and kind of the life that I wanted. And work-life balance is really big for me. And so I just want to let you know, if that is something that's important to you, it is possible to balance it all. So my sons are 1, 3, and 5. And when I'm not busy working at NASA, I am busy at home chasing them around. Some of the other pictures in the bottom left over here, this is my sister and I. We were getting ready for the 2017 total solar eclipse. And as you might know, on Monday, there's another total solar eclipse that will be crossing through the US. And so my sister gets to come out and hang with me for some of my work events, which is always a lot of fun. Moving over a little bit here, if you can see my cursor, this picture was me and my co-host Tahira. We were a part of the NASA broadcast for the eclipse that happened just in October, the annular eclipse. And I got to be on NASA TV and streamed on YouTube and everything. And funny enough, on Monday, I'll be doing the same thing with Tahira again in the same location, Kerrville, Texas. We will be a part of the NASA broadcast. So if you're not able to see the eclipse yourself, you can tune in, just search it on Google or YouTube, and you'll be able to find the link to watch the NASA broadcast. And then let's see, moving over in the funny white coats, that's my friend Dan. He's a part of our division in heliophysics, and Dan builds some of the really cool instruments that I was talking to you about. And so this was him and I just having fun in the lab when he was giving me a tour and showing me some of the work that he was doing. Again, my sister and I with a reindeer in the background. So this is a reminder for me that I also want to tell you one really cool thing about my job that I had no idea before I started working and becoming a scientist was that you get to travel to some really cool places, because a big part of doing science is effectively communicating your science and your science results. And that means talking to people all around the world. So for this particular picture, my sister and I were up in the Arctic Circle in Finland. I was there for a meeting to talk about results from a mission at Mercury, the messenger mission. And as a break from the meeting, we took a reindeer sleigh ride and we got to see the aurora borealis in the sky. So that was one of my most favorite moments ever. Another picture of me and one of my sons just in our matching NASA gear. And then finally in the top right, that's a picture of me holding one of our magnetic field instruments. And if you can see I'm holding this rectangular board, and at the very top, there's a little square thing that I'm circling with my cursor. That square part on the very top, that is the instrument itself. So this is a miniaturized version of it, and we were able to shrink it down teeny tiny. And when I was holding that, I was just shocked at how small it was. Okay. So now we're going to shift over to the Heliophysics Big Year, and I'll talk to you about that. So the Heliophysics Big Year is basically the celebration of the sun and how it influences everything in our lives. So I'll talk to you about some of the key milestones that we have as part of the Heliophysics Big Year, but we're really trying to invite everybody to get involved in your favorite kind of sun activity, whether that's some of the eclipses that we have coming up, or also just taking a moment to sort of reflect on how the sun impacts you and your life. It impacts our everyday lives in ways that we don't even think about. Something as simple as what you choose to wear on a given day, is influenced by the sun. Our art and our culture, there's many aspects to it. So if you go to this website that I have at the bottom or scan the QR code, that will take you to the Heliophysics Big Year site, where you'll see that every month we have a different theme, and we're just encouraging people to participate in the Big Year as much as possible. And we have 3 milestones that are a part of the Heliophysics Big Year. So it kicked off in October of 2023 with the annular solar eclipse. That happened back in October. And coming up on Monday, we have the total solar eclipse, which will be another big milestone for our big year. And then finally, in December of this year, the Heliophysics Big Year will come to a close when Parker Solar Probe makes its closest approach to the sun. And so we're cheating a little bit because the big year is longer than a year, so it truly is a big year. But these are the 3 milestones that we're really focusing on, the events that we just, have to make sure that they're front and center for the Heliophysics Big Year. Another thing that's happening over the course of the Heliophysics Big Year is that solar activity is picking up, and we will be reaching solar maximum. So the sun has an 11-year cycle of activity where it goes from what we call solar minimum, not much activity going on, not many solar flares, not many coronal mass ejections. You can see in these videos that I'm showing you here on the left, solar minimum, the sun just looks very quiet. There's not too much going on. But if you look over to the right, when we've reached solar maximum, it's that peak activity. You can see the sun just looks so much more dynamic. And right now, we are moving towards that solar maximum, and current predictions say that we will hit it sometime between now and the rest of the year. And so you can just see kind of all of these bright spots kind of flickering and firing off of the sun. And those are solar flares and those coronal mass ejections and other solar activity that I mentioned. So the slogan for the Heliophysics Big Year is "The sun touches everything." And what we mean by that is that it really does have an influence on us even more ways than we can imagine, whether it's the way that energy is input into our upper atmosphere. It can impact our ability to send a text message or email, taking some time outside, always a nice break in between classes or work is to just, get some sunlight, makes us a little happier, things like that. But I urge you to just take a moment when you have time to think about how the sun influences you in your life. So I'd like to point out the difference between the two eclipses, the two solar eclipses that we have during the Heliophysics Big Year. Now, back in October, we had an annular solar eclipse. And what happens when a solar eclipse takes place, the moon is moving in between the Earth and the sun. And when the moon moves between the Earth and the sun, the moon's shadow will be cast down onto the surface of the Earth. So when we're standing there and we look up in the sky, we can see the moon covering the sun. Now, for the annular eclipse, what happens is the moon is going to be slightly farther away from the Earth, so it doesn't block the sun completely. That means at the peak eclipse time, you're left with this ring of fire in the sky. We call it the ring of fire, and you'll see it kind of as this GIF moves over and recycles again. So we see this ring of fire effect, which I had the opportunity to see in October, and it was really fun and interesting. That was my first annular solar eclipse that I was able to view. Now, for the total solar eclipse, this is arguably more spectacular to see because the moon is a little closer to the Earth. And so when we're looking up at the sky, the moon will completely block the sun, and you're left seeing the corona, the outer atmosphere of the sun. And this is a region of the sun that we just can't see with our own eyes on a day-to-day basis. In fact, it's not safe to stare at the sun, but during a total solar eclipse, during totality, you are able to look up and see this upper atmosphere of the sun that we can't see on a day-to-day basis. And these are the paths of the eclipses where the moon's shadow is cast for the two eclipses. So with the yellow circles starting up in Oregon, coming down through Texas, that is the path that the annular eclipse took in October. The purple circles going from Texas up through Maine. Let me back it up. There we go. That's the total solar eclipse that will be happening on Monday. And so right in between where X marks the spot of these two eclipse trajectories, that's Kerrville, Texas. And that is where I was located for the NASA broadcast in October. And that is where I'll be located for the NASA broadcast on Monday too. So this is a special town, a small town in Texas that got to witness both the annular eclipse and hopefully the total solar eclipse. And I say hopefully just because it depends on clear skies. And right now the weather predictions aren't looking great, but we're all fingers crossed, holding our breath that it clears up for us. Now, I also want to take a minute just to talk about the fact that solar eclipses actually happen all over in the universe, and there's different science that can be done with these solar eclipses. And so, of course, it's amazing to just stand there and see them ourselves, but there's real science that NASA does with these eclipses. And I'll talk to you about the science that we're planning to do with the eclipse coming up. But what I want to point out is you've probably heard about exoplanets before, planets orbiting stars elsewhere in the galaxy and other galaxies. And our James Webb Space Telescope is discovering many new exoplanets. Now, one way that we study the exoplanets is by watching them eclipse their host star. So very similar, it is a solar eclipse. It's when the planet is crossing in front of the sun. It just looks a little bit different than the type of eclipse that we see here on Earth. Now, as the planet eclipses in front of its host star, what we can do is we see the change, and you'll see that on the left here as the planet goes by, you see the dip in the line. We see a change in the brightness. So it kind of takes a bite out of the brightness that we're observing with our telescopes, and it allows us to determine the size of the planet by how much brightness is going down, whether the planet has an atmosphere. We're able to determine the composition of the atmosphere to a certain degree. So in the astrophysics world, eclipses are used to do some of this type of science. Now on the right, I love to show this too because there's eclipses on other planets too. So Mars is a great example. This is a movie that, let's see, maybe I have to start it over. There we go. So this is a movie showing a solar eclipse on Mars, where one of the rovers, the Perseverance rover, used its cameras to capture the moon Phobos crossing in between Mars and the sun. Now, it's not as spectacular as a solar eclipse on our planet because it just so happens that the moon is the right size in the sky for us to completely block the sun, and that's not the case on Mars. So let's talk about some of the science that we'll be doing coming up for this eclipse on Monday. This is one of my favorite experiments to talk about. There's 2 experiments that will be flying on NASA's WB-57 high altitude research jet. So that's the jet that you see in the background there. We have 2 experiments that will be imaging the solar corona, that hot upper atmosphere of the sun. So what they'll be doing is taking images in the infrared and visible light so that we can understand the composition of the sun's atmosphere. We can understand how it's heated, how energy is transferred from the sun out into the solar system. And there's actually a population of dust around the sun that it's really hard to study that because the sun is so bright that we really don't have a way to study that on a day-to-day basis. And so during the eclipse, this is a way to look at that dust and also search for asteroids that might orbit just so close to the sun that we can't observe it normally. Some other science that we're doing, let's see. So there's going to be a listening party for amateur radio operators, so ham radio operators. Essentially what happens is when these radio signals are sent from one location to the next, they bounce off of the ionosphere. The ionosphere is a layer of the Earth's atmosphere that is electrically charged. And so these signals will bounce off and go to their destination. However, when the eclipse is happening, it changes the upper atmosphere of the Earth. And that means that it's going to change the characteristics of these radio signals. So we have basically people from the public who are trained radio operators who will be sending signals across the path of the eclipse in order to see how their signals change as the atmosphere changes with the eclipse. We have other experiments going on. The second one down, solar radiation effects on the Earth's upper atmosphere. This is another way that we're measuring that ionosphere layer where the charged particles are located in the Earth's atmosphere, just to compare how, I mean, essentially when an eclipse is happening, you're almost turning the sun on and off. It's an experiment that we don't normally get to do. So we get to see how fast those effects propagate through into our atmosphere. And then the other experiment that I have on the bottom here, bringing the sun's magnetic hotspots into sharper focus. So what we're doing here is using a radio telescope in California. It's measuring the sun, and the sun has active regions. You might know them as sunspots. They're dark regions that are cooler, that have really strong magnetic fields, and this is where different solar activity can come from. Now, those actually emit X-rays. And once we have this telescope pointed towards the sun, the moon will start to cover these different regions. So we'll see all the X-rays, and then the different regions will be covered by the moon so that we can actually tell which regions are giving off which X-rays. So it allows us to really understand where these radio emissions, not X-rays, coming from the sun, and what their sources are and how strong they are too. And then, okay, another really fun experiment to talk about. Now, we did this for the annular eclipse back in October. We're doing it again for this total solar eclipse. We are launching 3 sounding rockets to measure those changes in the atmosphere. So the Wallops Flight Facility is located in Chincoteague Island, and this is where we'll have the rockets launching from this time around. The rockets will launch, so this slide says 35 minutes. I think it might have been updated to 45 minutes before the eclipse, during the eclipse, and then after the eclipse, because what we want to do is send the rockets up to a point in the atmosphere where they'll measure the density, they'll measure the temperatures and different conductivity of that region. And we want to know what it is before the eclipse, during that peak eclipse time, and then after. And this helps us to understand really how changes in the atmosphere move around too, because this Wallops Flight Facility where we're launching, it's actually not in the path of the total eclipse. But as the moon's shadow moves across the Earth, the effects of it will propagate out almost like a boat going through the water, how you see the wake stretching out. We're trying to study what that is, how far that effect of the eclipse and the moon's shadow is in the atmosphere. Okay, and then I talked about the Parker Solar Probe mission and how basically Parker will have its closest approach coming in this December. So Parker will fly 4 million miles away from the sun, which sounds far, but it's actually close enough to touch the sun's atmosphere. It will be flying through that solar corona. Now, the Earth is 93 million miles from the sun, so we're going 4 million miles. It's going to get so close there. And Parker was launched back in 2018, so we're approaching about 6 years with this mission and its flybys. It had a flyby of Venus last August, and there's been a bunch of different scientific discoveries with this particular mission because it is the first mission to travel this close to the sun and the first mission to touch the atmosphere of the sun and of any star, really. And this is an opportunity for me to just talk about all of the different missions that we have in heliophysics at NASA. Now, heliophysics, as I mentioned, it's the study of the sun and its influence on everything. And so that means we need to have missions to understand every single aspect of that. And that's what we're showing here. Now, we have specific missions to study the sun, such as Parker. We have other missions that study the Earth's atmosphere and the Earth's magnetic field because we want to know how the sun impacts those regions too. And heliophysics also has some missions on Mars now. Now, for the Curiosity rover, there's an instrument that measures radiation on the surface. And this is a part of heliophysics now because we are interested to know when the sun sends out charged particles and radiation, how much of that can get down to the surface of Mars. And we're measuring that not only for understanding heliophysics science, but for the future of human exploration so that when astronauts go to the surface of Mars, we can help to keep them safe from the solar radiation. And there are so many launches that we have coming up in heliophysics over the next few years. So I'll talk to you for a minute or two about the AW mission, but that did launch last November. And then coming up this year should be Escapade, which I'll talk to you about in another chart too. And then you can just see we have a lineup of some really great missions that should be coming. Now, all of these dates are tentative because, you know, building missions and spacecraft are not easy. So sometimes these launch dates slip, but this is kind of where we're holding right now. And there's going to be a lot of exciting stuff coming down the pike for heliophysics. So AW is the atmospheric waves experiment, and that was launched just in November. It actually launched and went to the space station. So now it's sitting up on the space station. It was installed by the astronauts and collecting data. And basically what it's trying to do is measure the atmospheric gravity waves on Earth to determine how weather on Earth moves up in the atmosphere. So we care about weather on Earth in heliophysics because what's going on down below in the atmosphere will move up and that will hit the region where the sun is impacting too. So we need to understand what's going on above with the sun, but also below with the terrestrial weather. And so that's what the atmospheric waves experiment is measuring, is looking for gravity waves that are created by weather down below and transporting energy up into the atmosphere. Now, Escapade, as I mentioned, will be the next Mars mission. Escapade is right now set to launch in about October of this year, and it's going to be 2 small sats, so small spacecraft that will orbit Mars. And it's really exciting to have 2 measurements, 2 spacecraft measuring, because a lot of times when we have a single spacecraft orbiting a planet and measuring, we can't tell if certain features are occurring because it's a change in distance, or if it's a feature that's changing over time. So it lets us to understand when we see something, is it because there's a feature there and we're watching it change, or we're moving over it and measuring the difference, or if it's moving and changing. So temporal and spatial differences, basically. So it will arrive, let's see, it's not going to be April anymore. I think that might have changed, but basically it'll arrive in 2026 and has about a year of science that it will do. ESCAPADE's trying to look at how energy and momentum from the sun is transported into the Mars space environment, the upper atmosphere, and the magnetic field area of Mars. And I kind of gave a hint to this when I was talking about the rovers, but we are really interested in understanding space weather at Mars. And so when I say space weather, what I mean is we're talking about this activity coming from the sun that can kind of put out radiation and some of the energy from the sun. Now that can impact magnetic fields at the planets and especially Mars. And so this is something that we study at Earth quite often, but we're just starting to study it at Mars. What you're seeing here in this animation are actually particles of the Martian atmosphere that's getting stripped away to space thanks to the energy of the sun and those solar wind particles, so those charged particles coming from the sun. Now with MAVEN, we are measuring how the atmosphere is getting stripped away, but we really need to understand how solar activity impacts the Mars environment too, so that we can protect our astronauts, so that we can protect future robotic missions as well, and just so we can understand the impacts of space weather throughout the heliosphere. And of course, as I mentioned, there is space weather at Earth, very important. Now, one way that we can think of space weather has to do with viewing the aurora borealis. So the aurora are generated as charged particles from the Earth enter into the charged particles from the sun are entered into the Earth's atmosphere, charge exchange with oxygen and nitrogen, and then light up the sky just like this. Now, those charged particles make the aurora really entertaining to look at, but they can also pose threats to spacecraft that we have orbiting the Earth. They can also generate currents that then couple to power grids and have caused blackouts. And so space weather is a really big topic for us in terms of research, so that we can make sure that none of those things happen. And if we are doing our job correctly in terms of space weather, you won't even know when any activity occurs because your life won't be interrupted whatsoever. All right, and so this is where I'm going to wrap it up and say that's kind of a glance through our Heliophysics Big Year. You can see all of our different social accounts. Check out more information on the Big Year, especially the themes. And we have a solar eclipse coming up on Monday. So if you have any questions about that, I am happy to answer them too.
Okay. Thank you so much for the amazing presentation, Dr. Gibracho. So
You're welcome.
yeah, it was very interesting. Your presentation was not only informative but also engaging. Personally, I appreciate how you made some complex concept accessible to everyone in the audience. Okay, so if there are any questions from the audience, please type them in the Q&A chat box or raise your hand to speak. But I think I'll start with the first question.
Sure.
Dr. Gibracho, could you tell us where the interest in studying physics and astronomy comes from?
Okay, so how I first got interested in it. Yeah, so for me, I was one of those kids that basically said, I want to be an astronaut when I grow up. I always thought that space was really cool. Even though I said that, I didn't know quite what that would look like for me. So I started reading up on NASA a bunch. I went to different museums and planetariums, and that's where my interest grew. I took my first astronomy class in high school in 11th or 12th grade, and I absolutely loved it. So when I applied to college, when I went to the University of Pittsburgh, I was really interested in studying astronomy. And then I noticed that they had a program that was physics and astronomy. And I decided to take that route because I figured that with the physics background, that would open a few more doors for me than if I had just done astronomy. I also loved math. Math is my favorite subject by far. So that exposed me to a little more math as well. But it's something that I had always been interested in. But that doesn't mean that I knew exactly what I wanted to do. It was kind of that trial and error that I mentioned, trying out different opportunities and seeing what sort of research got me excited to figure out that, hey, I want to be an expert on magnetic fields and planets throughout our solar system. I had no idea that that's where I would be, but I knew that I was interested in space.
Okay, thank you. We have some questions here. Okay, we have a question from Amanda. She said, who/what guide you into getting into physics and astronomy? To my understanding, it's a hard major career.
Yeah, it is. It was very challenging. I would say for me in the beginning, it was my family that helped me, especially when I was younger. And I knew that I was interested, but not quite sure. So my parents guided me in a lot of that. As I went to college and got a little older, it was some of the professors. Honestly, finding a mentor that you resonate with is invaluable. It can be a professor at your school. It can be somebody that you meet networking elsewhere, but kind of having somebody that even just listens or shares ideas or lessons that they've learned is something that has helped me along the way. And I'm constantly, even now, looking and finding different mentors based on the different areas that I want to grow in. But yes, physics and astronomy was challenging for sure. There were times where I definitely, was nervous about being there or thought that I might give up. So I want to say, that's one of those instances where just keep pushing through and you can do it.
Okay, thank you. We also have a question from Maya. It says, what can science buffs in this area who are not in the path of totality look forward to during Monday's eclipse, assuming the cloud gods cooperate?
Oh, yeah. Okay. So, right, we talked about where the path of totality lies, but of course, in our area, that is not the path of totality. There will still be a partial eclipse that is visible. And if you have the chance to see that and the skies are clear, that will be an awesome experience still. There's an interactive map on the NASA website. The website is go.nasa.gov/eclipse explorer, or you can just Google NASA eclipse map and you'll find it. But anyway, you can go to that map, put in your location, and it will show you how much of an eclipse you'll get, what time that peak eclipse will be, so that you'll know what time you can go view it. And basically what a partial eclipse looks like is as if the moon has almost taken a bite out of the sun. So you get to see, it looks like a Pac-Man almost, or a crescent sun. You'll still get to have some of the changes around you that you'll feel too. So for instance, the temperature drops during the eclipse. Now, I believe in this area, the partial eclipse will be significant enough that there should be maybe a little bit of a temperature change. But even just seeing it in the sky, for me, it doesn't seem real when you look at it up in the sky. I often think, however many years ago when eclipses were happening and people didn't understand the science behind it, it must have been terrifying to see. And so I've seen one total eclipse and one annular eclipse. And both times I remember just kind of looking at the sky thinking like, it's so weird. If you can experience the partial eclipse, you totally should.
Okay, thank you. Also, we have another from Brian. He said, "Do you know what boosters are going to be on the Sounding Rockers launch on Monday?"
What experiments? Is that what the question was?
He said, "And do you know what boosters are going to
Oh,
be?"
what boosters? No, I don't know that. That is a really good question. Now, the project is called APEP, APEP. So you might be able to find out a little more information about the rockets themselves, but that's a good question.
Okay, so okay, we have another more from Jadiel. How long does the solar maximum last?
So the solar maximum, I mean, it's basically, you can think of it as a sine curve. It's not a regular thing in terms of it. We know that we always reach solar max, but the length of solar maximum and how high maximum actually reaches changes. I would say a few months to maybe a year or so. Even though right now we're on that increase going up to solar maximum in the solar cycle, we have a ton of activity going on. And we might even be in solar maximum. We just don't know it yet because we have to wait to see the activity go down. So there are solar cycle plots that you can find online, usually through NOAA. They're the ones that do a lot of the space weather activity for us. And you can check out kind of what historically the maximums and the minimums have looked like.
Okay, thank you. I have a question. So what could you say to students who love science or are interested in pursuing STEM careers, but think STEM classes are too complex to pass?
So I felt like some of my STEM classes were too complex. One thing that I've learned over the years is I've learned how I retain material the best and how I learn the best. So I think one thing that you can do is try to learn about yourself and put yourself in a situation where you're going to understand the information the best. Now, I am more of a visual learner, so I like to see things. If I have somebody just talking to me, I'm not going to retain it as much. So I really try to see things, to write them down, to revisit them, find out the way that you learn the best, and try to do everything that you can to kind of exercise that. The other thing I would say is give yourself more credit. I think we are our own worst critic, and in many cases, sometimes it takes a little extra hard work, but you really can achieve anything that you put your mind to. And that's something when I was growing up, I remember my mom consistently said that to me. You can do anything you want. And I thought, okay, yes, mom, you're going to say that to me because I'm your daughter. But I genuinely convince myself of that at some point, and that was a shift for me to realize that I can succeed. It might take a lot of work sometimes. You might have to work long hours, but if it's something you really love and you want to do, then you can absolutely do it.
Thank you. I think I have a few minutes to go. So here's another question from Amanda. And she said, "Are you into zodiac signs?"
Am I into what?
Zodiac signs?
Zodiac signs. Oh, no, I don't know too much about them, to be honest. I don't. That's a question that I get every once in a while. I mean, I will say, so in that first astronomy class that I took back in high school, we did learn about the constellations and how to find them in the sky. And I thought that was pretty fascinating. So that was one of my favorite things to learn about that. But no, I don't know too much about zodiac.
Okay. I have another question. So we know that NASA and private companies want to send people to Mars. So based on your expertise, does the planet Mars have a magnetic field? And if so, can it protect people from solar radiation?
Oh, great question. Really good question. So Mars has magnetic fields, but it is different than Earth's. The Earth's magnetic field covers the entire planet and protects us from some of this radiation. Mars has, we call them crustal magnetic fields. They're basically little umbrellas of magnetic field that are all over the surface in different areas. So it's not uniform whatsoever. And what we're finding is that they can deflect some of the radiation, but it doesn't make too big of a difference. So there are different ways that we're trying to mitigate radiation for astronauts, whether it's kind of creating a shelter that they would have to, go into if we give them notice that space weather is coming their way. I have colleagues at NASA who are looking at lava tubes. So they're going to Arizona and Hawaii and doing field work to study lava tubes and whether lava tubes on the moon or Mars is something that astronauts could kind of go into to shelter as well. So we're still figuring out the whole radiation environment at Mars, but that's something that's very important for our astronauts that we're doing active research on.
Yeah. Okay, so I think we don't have more questions, but we have last question from the Professor Thakur. Professor Thakur.
Thank you so much, Dr. Dubraccio. Thank you so much for this phenomenal presentation.
Thank you.
I have, and also for answering our questions. You mentioned several missions, and I would like to ask, sometimes our students want to apply for internships, and we are very hesitant because we think we are from a small school, community college, and we are not good enough to compete with others. And what kind of advice would you give us?
Okay. First of all, I would say absolutely apply. Myself and Eddie Gonzalez, we can give you information for internships. You absolutely are good enough. And that also goes back to my thoughts when I applied for my first internship. I had no idea, what my chances were. And that's why I put in so many applications, but all it takes is one. For me, when I was applying to internships, that was a time when the Ivy League schools really got a lot of the attention. And frankly, I felt very lucky as somebody that was, I was at the University of Pittsburgh. I wasn't at an Ivy League school. So I felt very fortunate that I had been selected. Additionally, at that time, many of my peers were men. And so being a woman and being from a non-Ivy League school, I felt like it was luck. Now in hindsight, I'm realizing it also has to do with my own achievements and hard work. Now, I will tell you, as somebody who works at NASA and selects for interns and internships, I make it a point to, number one, focus on diversity. Number two, I feel like, getting my foot in the door was that opportunity that I needed to accelerate my career. And I love giving people from all different backgrounds and all different educations that opportunity too. So that's definitely something that I look at. Also, when I am selecting for internships, I actually hide all of the identifying information that I can. So I hide the person's name, I hide their email address, I hide their school, anything that would, even unconscious bias lean me one way or another. I redact that information because I want to see who's putting the best application forward, who has taken the time to read what I'm advertising and respond to it. Don't give me a generic response of I want to work at NASA. Show me that you're looking at, okay, I want to work in the heliophysics division because I'm interested in studying magnetic fields. And I see that you've taken the time to do that. So those are, if that helps, that's kind of what I look for. I really try to make an unbiased decision because I want the best person for the job.
Thank you so much. This really helps a lot. And
Great.
students in the audience, please follow this advice, okay? This also helps us prepare for future, not just for internship to do our homework.
Yes. And don't be afraid to reach out directly to people too. If you find a NASA scientist that you're really interested in their work, email them. I know it sounds really intimidating and out there, but frankly, when I have somebody go out of their way to email me and ask me a question or ask me for an opportunity, I might not always have an opportunity to give, but I will then try to connect them with somebody that does. Because if somebody goes out of their way to really make that effort and talk to me, I make it a point to try to help them. So don't be afraid to just reach out and cold call people too.
Thank you.
Okay, I think there's no more questions. So thank you so much, Dr. Dibraj, for joining us today and
Thank
sharing
you.
your expertise with us.
Thank you so
yeah.
much. Yes.
Thank you all for having me. It was great to talk with you.
And all the best for a good solar eclipse and no clouds and so
Yes,
on for all of
fingers
us.
crossed. Yes,
Yeah.
everybody, clear skies.
Okay,
All
thank
right.
you.
Thank
Thank you so
you.
much. Have a good day.
Have a
You
good day.
too.
So don't forget to complete the survey. You can find the link in the chat box. And yeah, we will conclude our session for today. So have a wonderful day, everyone. So see you next time.
Thank you.
Thank you.